Introduction. So I'm the last talk of Voneka. So I
the last submission.
Oh yeah. It was after the deadline, I guess. So I try to be quick so we can start the weekend sooner. So but let's start about what is my project and what is the motivation behind the problem that I try to solve. So I come from a group that we are mostly interested in mobile edge computing. So we believe that for the coming couple of years, these applications, latency critical applications that are gonna be run on the wireless links, they're gonna explode. So what we see like for TSN currently, which is really a hot topic, and we expect that at some point we are going to see an extension to wireless links, but that is a very challenging task, so to say, and this is what we are mostly interested in. So we think that these applications, they are categorized into two different branches. First, human in the loop applications, assume like AR headset, VR headset, but wireless, right? So when you're wearing an AR headset, when you turn your head, there is a sensor on the AR headset that tracks that motion. It sends the sensor data to the cloud or edge. And then the feedback comes back and you see just the augmented information on the glass. So if this round trip delay is not bounded, you will feel like that there is a lag, and this really affects the quality of experience. On the other hand, we have cyber physical systems like industry automation, like everything that involves a control loop that could be run on wireless instead of wires, right? So this end-to-end latency is critical. So either we are, for example, running a PID controller or a model predictive controller at the server, and we want to have wireless links to, I don't know, some sensor and actuator in a plant. This end-to-end delay is really important, as we all know. So, but the key thing is that wireless link. So how can we deal with this unbounded end-to-end latency or latency in the wireless link when we have such a network? Definitely the answer is a probabilistic bound, right? So what we know from the channel model in the wireless domain is that, yeah, the latency is unbounded. You cannot define a maximum for the delay, but we can define probabilistic bounds. So 10 to the power of -5, this will be the maximum latency that you get, for example. And recently there is interest in integrating like 5G links or 6G links or new generations of Wi-Fi with TSN. So this is quite a challenging topic, and which is needed. So what is the model that I resort to? So I see this end-to-end link as a tandem queuing system. So, and I see the sensors at the end node. So they are deterministic arrivals. So we have a row, and then we have like K queues with service curves or service processes. And as I say that for task N, I think I say this is a task flow. It's not a packet, because you can imagine a case that you are sending like sensor data to the server, but server generates like a frame of a video, right? So this is not one packet that goes, and then the answer is not one packet anymore. So we say it's a task. So this end-to-end delay of task N, as we know, like queuing delay, the service delay, and so forth. And what we are interested here is in the service time. So the service times in the wireless links, or the service curves in like network calculus language, how can we obtain them? How can we devise these service curves or a service process? What is the assumption? So the problem formulation, in a sense, would be for me to predict or estimate the delay violation probability. for each packet or for the flow. If I say for each packet, this would be like a transient DVP prediction. If it's the flow, it will be like a stationary DVP probability prediction. So the probability that the end-to-end delay is greater than tau, which is the delay target, given, yeah, the first expression explains that the packet or the task is in the network. And the second one, xt, is the important one, because I am conditioning this probability on the state of the network. And this gives me the freedom to model anything there. So I can say, all right, xt would be like arrival characteristics. Like I can define xt as rho, right? And this will give me like the delay violation probability in a stationary manner. Or server characteristics, like the average SNR of the link, right? Again, this will give me a stationary DVP, right? And then for the transient notions, if you want to use, for example, we can use backlogs of the queues, right? So Qt in that sense. What are the related works on the network calculus domain? On the wireless links or fading channels, there is this work by my dear teacher who's present here, Al-Zubaydi et al. So they investigated this problem by and they analyzed and produced a solution which they call min-X algebra, and through several transformations they could actually introduce bounds on the Rayleigh fading channels, multi-hop, and in a stationary manner. Then my friend Jaya Champati, they extended that work for transient analysis, and they introduced this XI here, which will be the backlog of the queues. So for the multi-hop case, assuming that we have certain backlog, what would be the delay violation probability? And you can, at every point in time, you can have different backlogs. So you, at every point in time, you can have a different DVP prediction, right? So that's why this is transient analysis. But what we are interested in, and I really want to motivate it in a good way here, is why now I'm gonna go for the data-driven approach, a data-driven approach. So I saw in one of the presentations a work on the trade-off between tractability and the tightness of the bounds in network calculus. And I think that shows itself really much in the wireless links. So here is the simulation of simulation results and the bound results of the previous works that I've shown. This is the stationary case for the Rayleigh fading channel with like 5 hops and 10 hops. I show them with the row of 20 bits and the average SNR of 5 dB and 3 dB. But what we see here in terms of millisecond, there is a considerable gap between the tightness between the bounds and between the actual curve, right, or the simulation. But and what do we why do we care about this? So we have two main goals. First, if we can do some optimization on the wireless links, in a sense that we could schedule resources, we could manage resources in a better way, and we don't want to waste a lot of resources. That would be our first goal. Second goal would be if there is any way of guaranteeing this end-to-end delay in a probabilistic manner. So maybe we could say that, all right, we can stay with the bounds because they can follow the decay rate for the optimization purpose. But then, because the gap is there, and the most important thing is that these are based on the assumption on the service curve, which is a Rayleigh fading channel, right? So, and Rayleigh fading channel, how often can we rely on a Rayleigh fading channel in everyday use cases? When you move to different scenarios like industry, wireless scenarios, the channel, there is a different channel model. When you move to like line of sight, millimeter wave, there is a different channel model. this is what makes us to move towards a sort of a data-driven approach. So what if we could, for example, have an algorithm to give us the service curve based on the data? And not only the service curve, but we have some measurements from the channel like SNR. How can we relate these figures, relate these numbers to the service curves? This is, of course, not what I'm doing in this work. This work is the first step towards that. This is a proof of concept to see what can I infer from the data. And I try to use the simulation data and make a model so I can give an estimation for these curves, for these delay violation probabilities. And I resort to, and this problem in the frequentist statisticians is called a conditional density estimation. Perhaps you have seen that you have a data, which is, for example, you have a stationary process and you can fit like a Gaussian mixture to that data. This is the core of the solution. We fit distributions, parametric distributions to the conditional data. And these conditional data, these conditions, they come from that X. So if X is the average SNR, I gather traces from the network, end-to-end delay traces from the network with different SNR values, and I can fit this Gaussian mixture to those conditional data, right? For each condition, I can get a different parameters for those Gaussian mixtures, like different average or different mean or different variances. But this doesn't work. In our latest publication, we show why this is really inefficient. But there is another thing. So once we have these conditional parameters, how can we relate them to the actual information from the network? For example, I have the backlog, I have the SNR information, and on the other hand, I want to have these parameters condition on these values. How can I relate them? And there is a solution in this domain called mixture density network, which uses a neural network. So basically a nonlinear estimation of the nonlinear function that can relate this condition of the network to those parameters. And if I have the data and if I have a relatively large data set, I can train this neural network to give me the proper parameters for every condition that I can tell. So I estimate that phi, which was the DVP, with the probability of the delay, end-to-end delay of the network. So this will be the structure of the predictor. So we will have the xt, which is the condition of the network at time t. Then we give that to the neural network, which is trained. And then there will be have a parametric PDF, which, as I said again, you can refer to the paper. We chose to use a Pareto distribution for capturing the tail behavior. So we found out that Gaussian mixtures, they are really inefficient and they are unable to capture tail behavior. So you see here what for fitting to the data, for the bulk of the data, we are using Gaussian mixture or gamma mixture because it's the delay. So it should be positive. But for the tail, we use another distribution which can capture the tail decay. Like I'm talking about 10 to the power of -1 or 2. After 10 to the power of -2, it can capture the tail behavior in like 3 parameters: one tail decay, one scale, and the threshold. And I can train the whole system using expectation maximization. I know that compared to network calculus, this is just an estimation. There is no guarantee, there is no bounds, but in the future work, I tell you what I'm planning to do with this. So first set of results for what I've done was to, for all these different parameters, so different arrival rates and different average SNRs. I trained this model with the ample amount of samples, 10 million bits going through this 5-hop Rayleigh fading channel, okay? And you see these are the, can I use this? Oh. Yeah. So this is the bound in the case of 5 hops, 4 dBSNR, and 25 bits per second per milliseconds. And you see this line, this orange line is the simulation with the circle markers, and with the triangle markers is the data-driven model of mine, which is quite, I mean, you would expect that. I gave it like a lot of samples. You can expect that training samples could come up to here, something like that, right? But the beauty of it is that once I reduce these number of samples to, like I show in the next slide, it really performs well because of that. And we believe it's because of that Pareto distribution that we put at the tail. And on the 10 hops, we see that with more hops that we have a loser bound, unfortunately, but still our model can follow the simulation data very well for either of those cases. Still, there is some gaps here and there, but it is fairly accurate. But I repeat again, this is not a performance bound at all. It's just a, but for sure, this maybe could be used for optimization purposes and not for guaranteeing stuff. Then I reduced the number of samples from 10 million to 8K, 6K, and 5K. And we see what happens. So we were expecting if we give less and less number of samples to this model, we would get a looser or yeah. So in this case, we are still very good in terms of accuracy. So triangles is our model. The circles is the simulation. And when we reduce the samples, there is a threshold that after that, it kind of falls behind. So it cannot follow the data. And this was expected, and this is one of the disadvantages of this approach. You cannot, and what is this limit? This would be an interesting question. At which limit my model is not accurate anymore? And we were investigating like Bayesian networks for finding this. So maybe in the next, in the future works, we would investigate that more. Then we, for the transient case, what I showed you was for the stationary case. And for the transient case, X here is the backlog in the queues. They are equally distributed in the 10 hops of the queue. It's the Rayleigh fading and the wireless channels. And what we see, again, the same trend. The data, actual data-driven approach follows the simulation very well. And in this case, well, yeah, the bounds are not that loose, which is good. And what I wanted to mention here was that, yeah, so we basically trained one data-driven model for all these parameters. And we give it like X as like 500 or 1000 or 1500, and it gives us the DVP. What is a little bit, I don't know if someone noticed. So the blue curve you see, the prediction of the model is very bad here, right? I did this intentionally. So what I did was to train the model only on the data of the orange curve and the green curve, okay? And because once you have this neural network, you're expecting some sort of generalization. So you would expect some sort of a regression going on. So when it sees like 1500 and 1000, when you go to 500, you would expect the neural network to like generalize that and give you estimation somewhere here, right? But that is not the case here. And it shows another disadvantage, which is when you have the training data, they should really cover the entire condition space, right? Otherwise, this thing doesn't work. So the conclusions, yeah, a data-driven network DVP estimator we introduced. We compared it to stochastic network calculus, state of the art for wireless links. We saw that they really suffer when the data samples are limited. And for the future work, so I'm really interested to try and see if using the data, we can find out a way to produce these service curves of wireless links, like because they change a lot, the model underneath changed a lot. What if we could gather samples using this extreme value theory and this model, we could produce these service curves online, like by collecting traces online, and then step into the guaranteeing domain, right? And then, yeah, we are gonna move to a practical setup. We're working on a test bed to benchmark these DVP predictors, both network calculus and the data-driven ones. And we would like to use these predictions in resources scheduling of time-sensitive flows. Thank you very much. Yeah, the simulations and stuff, they are all on GitHub. If you're interested, you can have a look.
Thank you for the last talk
Mm-hmm.
of Monica. Last chance for the audience to ask questions. We have time for them. First of all, please. Thank you for
Mm-hmm.
So the parental behavior, where did that come from?
Well, in the Rayleigh, yeah. So we have a question about the extreme value or Pareto distribution. Why do we use Pareto distribution when we know that it's exponentially decay, right? Exponential decay is happening. The answer is that, yeah, in the Rayleigh fading case, maybe yes, but I'm thinking more general. So I think if I wanna build a model for some other link with, like, I don't know, millimeter wave, non-line of sight whatsoever, I could get a very, non-exponential decay rate. And what will happen? Can I capture that data? In the paper, we actually make a good analysis of that. So with different tail behaviors, this Pareto distribution can really capture the tail decay in a better way and more efficient way. So yeah, in the Rayleigh case, yeah, maybe we could do. Sorry. Yeah.
Your neural network is really good, then you're going to overestimate that curve, basically.
Yeah. Mm.
Or if it is less, if you take this.
If you do overfitting, it can underestimate. Exactly. But it is for sure the best distribution for capturing the tail behavior. That is for sure coming from the extreme value theory. It is proven to be the best and most efficient distribution. Like when we talk about the average behavior of, we go for Gaussians. On one pocket, you must have the Gaussians for capturing the average behavior of random processes, but on the other pocket, for the tail behavior or very rare events and tail behavior, GPD or generalized Pareto distribution is the one that one should refer to, one should use. And it's not only able to capture tail decay when there is unbounded latency or unbounded distribution, but also it can estimate if it is really bounded. So there is a parameter that if it's negative, then there will be a maximum, and it can capture that as well. So it's really powerful. Yeah.
We have a question by Amr as well. Please.
I actually have a more basic question because I didn't get the beginning. I think on slide 7, you had a problem description, and I
Yeah.
don't really understand what are those
Here,
Seven.
7. Here.
So what are those parameters, theta t, that you are?
So theta t is the parameters of the distribution. So I will have a parametric distribution. I must have a parametric distribution that the neural network will estimate those parameters, right? So for example, Gaussian mixture, Gaussian mixture with like n elements, it will have n means and n variances that you need to estimate, right? So the neural network in the middle with the weights omega here, it will convert the conditions of the network to those parameters. For example, if the network is really crowded, so you have lots of backlog, the mean values, I would expect that the mean values would be really high, right? So you would get a larger end-to-end latency.
These parameters, they are the parameters of the conditional probability.
Exactly.
All right. And what is the input to this?
So the data set, you mean? The data set that we form, they're in this format. So X1 will be the condition, Y1 will be the end-to-end delay trace, the actual end-to-end delay. So we get these traces from the packets that traverse through the network, from the flow paths that we have. Like they should be time synchronized. So using the timestamps and so forth, we can have end-to-end delay with the condition that that packet had observed, right?
Okay, thanks. As session chair, I take the liberty for a last comment question. On slide 11, you showed us on purpose, which is nice, that the generalization does not.
Yeah.
Having used neural networks for something entirely different, we were asked that, and it worked. And then on slide 10, you said that with increasing size of the training set, there's this relation that your predictions will become better. And we were asked, how long does it take to create a training set until we find a minimal set? Exactly your question. And here we had also the reverse in our problem setting. It just didn't work. We didn't have this relation. So it's just this comment about, I think this is not general observation that can be generalized to other works, but it's super nice to see that this works for you, that you increase the set and you have this real increase of prediction accuracy. Very good, nice. So no question after that. Then I can close the session. Thank you all.
Thank you very much.